We're really happy to restart the seminar series. It's been a while. It was started 5 years ago, maybe exactly 5 years ago by Emiliano Lorenz and Yang Zheng. The goal of those series were to introduce people around the world and researchers to interesting, exciting topics in privacy and security for machine learning. 5 years after, all the people that have been invited are doing really exciting work in this area of new and upcoming distrustworthy AI problems. So we decided to continue the series under the new idea of distrustworthy AI framing. And we're very honored to have uh, our speaker, today's speaker, Peter Kairouz. So he's been incredible. I've known him for maybe more than seven years now. He's been incredible researcher and mentor for me. And so he's currently a senior staff research scientist. He leads a bunch of incredible work and research initiatives. So he pioneered many areas in federated learning, in differential privacy, in privacy auditing. And in his background, he got his PhD from UIUC, and then he also did a postdoc at Stanford. He has numerous awards, including the Best Paper Award at Sigmetrics, Qualcomm Innovation Award, and CCS Best Paper Award. And he recently got Information Theory Society James Macy Research and Teaching Award. Uh, uh, um, I'm very happy, Peter, that you're able to join, and please take away.
Yeah,
Thanks.
thanks a lot, Eugene, for the generous introduction, and it's always been fun to work with you. Hi, everyone. I'm very excited to be here. I was debating a lot, what do I want to talk about? There's just so much that our team at Google is doing. And then I settled on this topic because I feel it's so important and still very open in many ways. And I'll try to highlight some of the open questions as I go in this presentation. And really, if you want to take one message, is that really the context matters a lot. This is more generally, I guess, not just in the context of synthetic data generation. You'll see over and over. And this is, a collection of papers that I'm going to present with a collection of people. I'm highlighting a few key collaborators, but there are other people at Google that have contributed to the shaping of the narrative, to the work that we do, to our product launches. So too many people to list on even one slide. So before I dive into the core contributions of the work, the main observation is that we've really trained very powerful LLMs on pretty much the entire web data. What do we do now? What do we do with these powerful LLMs? And what a reasonable person would say is, I'll try to make the best out of them. I'll try to use them. We've all been using them. And there are a few very successful use cases of them, like coding and searching for information, doing these deep search or research API calls, and they work nice for those. But when you start infusing AI into lots and lots of different products that people love and use on a daily basis, like email, docs, sheets, travel websites, so on and so forth, even an overleaf for us researchers, you quickly discover that, even though these models are very strong and very powerful, they don't work as well there. There's something that's still missing. It's not hitting the bar. I've had very bad experience with integrations of Gemini and also integrations of GPT with products from whether it's Microsoft or Google or other companies. And so really, if you think about it, the reason why we're having such bad experiences is because when you look at these models, they're really trained on a lot of open source data and vendor data from articles on Wikipedia, maybe news websites, blog posts, open source code on GitHub, so on and so forth. But then we take them and we infuse these models into products that deal with medical patient data, biometric data, financial data, calendars, chats, emails, maps, so on and so forth. And no wonder why these integrations are not as successful or not as pleasant to use, because there is a distribution shift between the type of data, whether it's in the modality of the data or just in the structure and statistics of the data relative to the data that these models are trained on. And so this is very important. And what's happening is that all the companies that are integrating AI features into their portfolio of product are realizing that this is no different than the usual cycle of product development. So here's a very simple example of an AI-powered travel agent. Say you take one of the state-of-the-art LLMs, you integrate it into your travel agent. So we're starting here at the bottom left corner of the cycle. And you deploy the AI features. Maybe it's an agent that helps you book all sorts of trips, whether it's leisure, work, business, so on and so forth. And so then you have consumers using this feature, connecting it to their email, to their calendars, to their preferences via documents or sheets, chats they've had with their loved ones or colleagues at work, so on and so forth. And then what you're going to do is you're going to collect data in the form of interaction data with this AI feature. So we're going to look at model inputs, what went into the context, what was retrieved, the profiles of the people. You're going to look at the outputs of the model. You're going to look at the feedback that people gave, whether they liked the performance of the model or not. Sometimes they literally write down feedback that it was offensive, not correct behavior, or they try to even correct the behavior of the model. And then what you do with the interaction data is you take it and you try to evaluate the performance. How well is this AI feature? How many people are using it? What are they using it for? When is it failing and why is it failing? Broadly, how do I improve it by either redesigning the model or just improving the user experience and user interface? So really what we're looking for is either insights to inform us about usages, failure modes, and potential for improvement, and also then maybe data in the form of synthetic data that helps us improve the models. And I want to, double click on the insights one because it's an interesting one. Doing insights on Gen AI type data, which is largely unstructured data in the form of screenshots, so images or text, is something that is actually not that trivial. You may have heard of Anthropic's Claude Insights and Observation system, where they start by taking conversations with their Claude chatbot, and they extract these short summaries that are called facets, essentially keywords and a simple description of what the conversation is about. And then they compute embeddings on these facets, and they use a hierarchical clustering approach to cluster these different facets across the conversations. And once they create these clusters, they drop the clusters that have very few conversations attached to them, and they keep the clusters that have many conversations in them, above 50 or something like that. And then they go and they summarize the contents of the conversations that fell into each cluster. So it allows you in this very nice kind of user interface way to understand what people are using Claude for. For example, how many people are using it for programming, how many people are using it for art and design, education, so on and so forth. And you can double click on each cluster and zoom in and know amongst programming, what are people doing? For example, are they doing web development? Are they doing numerical simulation and analysis? Are they using Python or C, so on and so forth? So it's very powerful and it's very interesting, really nice work. However, as we are good privacy and security researchers, we can ask ourselves, can we actually take the outputs of Clio and somehow exfiltrate private user information? And the answer is actually a resounding yes. And in fact, you don't have to work really hard to show that you can attack Clio. And this is a talk for another day. This is a beautiful work that I did with Emiliano and Sundar, his student. And so maybe they will present it some other time. But take my word for it, these types of insight systems are fundamentally broken from a privacy perspective. So how do we go about doing it in a privacy preserving fashion? One solution that my team recently announced is to use a combination of a confidential computing space in the form of a trusted execution environment, where you upload all the user data in an encrypted fashion. Of course, the service provider would not be able to peek into the contents of the data because they're encrypted using a key that is etched to the device, which is the secure enclave. And then inside the secure enclave, serve an LLM analyst in the form of, let's say, Gemma in this case, which is open source, analyze the conversations, extract features from them, cluster those features if you want to cluster those features, or build all sorts of distribution models on them, apply differentially private statistics on those derived features to aggregate across users, and only release the DP insights and statistics. Of course, the techniques that we've used are extremely basic. We're essentially extracting one-dimensional features from these unstructured data files, and we're then building a simple histogram and adding DP to it. So nothing fancy at all here. What's very interesting is the fact that we can run a multi-billion parameter model in a confidential compute space, and then we can do large-scale aggregation across millions of users and add differential privacy before we release the output. So this is something we talked about. It was a joint work with the Pixel Recorder team. So this is the Recorder app. And the AI features that are trying to infuse into this app are features that allow you to automatically summarize all your recordings on device, to get action items list, and to also get all sorts of insights into your own recording and ways to improve. For example, if you're preparing for an interview or you're recording a podcast, so on and so forth. And what I'm showing you here on the slide is a sort of like a heat map, two-dimensional distribution that we learned about the topics from actual user recordings. So this is literally representative of the true accurate distribution. The size of each box that you're seeing here is proportional to the number of usages across the Pixel Recorder user base. And this was learned using this technology that I just showed you with epsilon equals 1. This is not the only technology. We have another research paper called Urania that does literally what Clio does, but with DP. So it uses clustering at its core, and it does DP clustering on embeddings. So this is just to tell you that there is a way to get insights with provably private guarantees in a formal and proper manner. And this is an important piece, but it's not a solved problem. So deriving rich and hierarchical private structured insights remains a widely open problem. All these solutions that I've just talked about are extremely basic, and we still don't know how to get this deep, hierarchical, rich, structured summarization of unstructured data in a provably private manner. We don't even know how to evaluate the performance of these algorithms, because getting even a ground truth is very difficult in this situation. You start with unstructured data, you end up with something like tabular metadata, or features that have some sort of hierarchy into them. How do you even validate that you did a really good job, that what you've extracted and anonymized or privatized is indeed correct? You don't have a proper ground truth. So lots of interesting open problems for those who are interested in this space. One thing you'll notice in this talk is when I say insights, I'm really referring to a couple of things that are closely related. I'll just use them interchangeably. So structured summaries on unstructured data, or metadata, or structured metadata, or tabular features, they're all going to mean the exact same thing. So just, keep this mapping in mind for this talk. Great. I mean, we didn't solve private insights, but I gave you a glimpse of a path towards solving it and some very introductory approaches towards solving it. So if we go back to our example, the AI-powered travel agent, one might wonder, now with these insights, what might you do? maybe you'll discover that the app is not working as well as it should be. A lot of people are, not using it, or if they're using it, they're not happy with it, or it's failing on some use cases, some trip entries of some form or some type. And so you might wonder, can I actually improve this service? Can I improve this integration? And once we get into the improvement phase, we stop being in the evaluation phase, in the observation and evaluation phase. We start needing data to improve. That's the natural course of action here. And so this is where we need synthetic data in order to make this integration a better one. And so then the question is, how do we get the synthetic data in a way that's also privacy preserving? First of all, we can ask ourselves, why do we even need synthetic data? Why not just train the model of the AI-powered feature directly on the data of the app itself? And you could potentially do it with DP. The issue with that is that you want data that's inspectable. You want data that you can literally potentially look at and figure out, oh, I understand why the application is failing because the prompts look like so. They have the following structure to them, and people are, exploring such and such and such. So you want data that can be used potentially for many things, many forms of downstream applications. Maybe today you built this feature, tomorrow you're going to build yet another feature into the same app. You don't want to suddenly, for this other feature that you want to build, redo the whole private training of this new model. So it's versatile. It allows for inspectability and for debuggability and for being applicable to multiple downstream tasks. And with DP, we know how to privatize it, and we're starting to see improved performance of differentially private synthetic data. If you'd like to learn about anything related to DP synthetic data, check this manuscript that we put up late last year. We're going to update it in a couple of weeks. So if you wait a couple of weeks, you'll see a refreshed version of it. But it's really, really good introduction to DP synthetic data. But really, the main two approaches towards synthetic data are either you do what's known as differentially private fine-tuning, where you take the data, you pre-process it, you filter it to retain the high-quality data that's relevant to the sorts of downstream applications that you care about, and then you bound how many examples you take from any individual user, and you run what's known as DP-SGD. Hopefully, DP-SGD is something that is very common to people who are watching this talk. If not, raise up your hand. I'm happy to walk you through it. But it's a method of training models with provable differential privacy guarantees. And the idea is that once you've fine-tuned a publicly pre-trained model with DP using DP-SGD, you get this DP-fied generator that you can then bulk prompt and create DP synthetic text from it. So it's a fairly complicated process. As you can see, there are a lot of steps, but it's an art that keeps improving because the algorithms for DP are improving, the pre-trained models are improving, the size of the data is improving, and then the way we prompt these models is also improving. So the quality of the synthetic data is improving by the day. So that's one main approach for creating DP synthetic data. But this one requires training, and sometimes it requires training multi-billion parameter models, even if you use parameter efficient fine-tuning. So the other approach is called private evolution. Xenon Lin and his co-authors. And this one is actually quite interesting because it does not require any gradient computations or any training. It in fact relies on just public API access to very powerful models. What you do here is you start by having a synthetic set of data, and this can be random data or something that you obtain by prompting public models using prompts that describe the application at a high level. What you then do is you compare your synthetic data to your private data. using embeddings and L2 distances and nearest neighbors. And you form a histogram that maps every synthetic example to its nearest private example, or the other way around. And you deepify that histogram using a simple Gaussian mechanism or a Laplace mechanism. And then you take the top entries as a signal of these are the synthetic examples that are most representing my private data. So you go back to the LLM and you tell it, I want you to generate more of these synthetic examples. And the LLM rewrites those examples, gives you variations on those examples, and you cycle back and you repeat this process. And usually you do it about 10 times. You can do it about 20 times, and it converges at one point. And that's how you take the final synthetic data set and you call it a day. You say, I'm going to work with it as a proxy for my private data set. So it's very simple. It just uses DP histograms. It does not need any fine-tuning or gradient computations, especially on large models. And it has the potential to tap on closed source proprietary models, which is really nice because you could use some of these powerful models. All right, so these are the two methods we have for generating synthetic data, but they have drawbacks. The first one is that for both approaches, we have a very limited way to steer the DP generator to give us data that follows very rich schemas. So we don't have a way to control the outputs of the model in a very nice way. We don't even have a way to insert those schemas and learn those schemas in the first place. So these approaches don't allow you in the first place to automatically learn those rich schemas that can be used to then generate according to what you really want. For example, as you're seeing in this example, I'm trying to create an email and I'm trying to set the token count. I'm trying to set the sentiment of the email, the tone of the email, whether it has an attachment or not, so on and so forth. So that's one drawback. We have to live with the generated data that we get from these generators. The second one is that we often get an imbalanced representation of the features that exist in our underlying data set. So for example, if we start with a data set that has roughly equal sentiment distribution, we either tend to upsample some of them or downsample the others. And that is a common observation that we saw by using these models, because these models have their own pre-training bias that's going to also push the model to go in certain directions and not just that fine-tuning, let's say, phase that is being used. And lastly, when we generate synthetic data from these generators and we try to compute the distribution over the synthetic data that's generated and compare it to the distribution of the private data, there still is very high mismatch between these two. And we can quantify it using something like the MOF score if you've used it, which is just the KL divergence between low order representations of these distributions. So these are some of the drawbacks that we would like to fix. And I'll show you the idea of how we can fix them. And before I show you the idea of how we can fix them, I want to tell you that in the first few slides where I talked extensively about insights and metadata and structured summarization, that was literally the thing that we needed in order to fix these types of drawbacks. And the idea is as follows. You start with text data. This can work for non-text data, but I'm focusing the whole talk on just text data for the sake of simplicity. And you then extract the metadata. This is exactly what we talked about when we saw the insights piece. You could be doing clustering. You could be prompting a model, asking it to extract multiple features, potentially hierarchical features using schemas that you come up with based on your understanding of the application. You could potentially use public data here, but you really need to extract deep, rich, hierarchical, tabular metadata. So you have to do this structured summarization step. So far, I haven't done anything with privacy, and that's why these two boxes are still in red. They're locked. They're both privacy sensitive. So now what we do is we actually compute a DP-fied synthetic metadata generator. So this is a different kind of generator. It does not produce unstructured text data. It produces structured metadata. And this is an easy thing to compute because either it's essentially using a marginal-based DP approach or more complicated approaches. You may have heard of AIM, which is developed by Ryan McKenna, a colleague of mine at Google, and his co-authors. There are state-of-the-art simple mechanisms that are not, heavy on the fine-tuning or anything like, computing gradients on large models. Very quick, very efficient algorithms for computing DP-fied synthetic metadata generators. So that's the first tweak we're going to do. The second tweak we're going to do is that rather than training a DP-fied generator, we're going to train a conditional generator. So if you go back to the fine-tuning, we're going to condition the model by inserting in the context the metadata and telling the model how to generate text data that follows precisely that metadata. And there are lots of ways of doing it, and I'll walk you through two canonical ways in a bit. But once I have these two objects, the DP-fied synthetic metadata and the DP-fied conditional generator, combined together, I could generate metadata, condition the generator on that synthetic metadata, and ask it to generate synthetic text. And this is really why I'm calling this talk Context Matters, because I'm really leveraging the power of the context to generate higher quality, more representative, more diverse, and more controllable synthetic text. And that is really, the main point of this talk. So you can stop here and I think you would lose almost nothing. But if you're curious enough, we can keep going. And what I'm going to do in the remainder of the talk, in the remaining 24 minutes, is I'm going to try to walk you through two settings. One setting, which is if you have enough compute power in order to fine-tune a large-ish model, a multi-billion parameter model, how would you incorporate the metadata? And then I'll show you very briefly how you could incorporate the metadata if you don't have fine-tuning ability, if you only have LLM API access ability. So let's start with the first one. And this is a paper that's called ACTG-ARL. Yu Jung, who is the main author and the primary contributor on this one. So again, the assumption here is that we can afford fine-tuning a billion-sized LLM. We can also leverage state-of-the-art LLM training and inference. And we have API access to powerful closed-source models. So let me show you how we're going to do this. And it's going to have two phases in them. The first is we're going to leverage everything we talked about, which is the whole DP fine-tuning stack. So this is what I presented before. Keep it in mind. And we're going to start with the first phase, which we call the learning phase, where we take the private text, we extract features. Again, features, metadata, structured summaries, all are equivalent. And I'm showing you an example here of I'm extracting the medical specialty, the clinical focus, the patient agent group, so on and so forth. So these are structured tabular features that I've extracted from papers, medical papers in this case. And what I will do is, from the extracted metadata, I will use the DP fine-tuning modified so that it is DP conditional fine-tuning. So this is the middle box in green, the DP conditional generator. It's literally what we do in DP-SGD, except that everything now is conditioned on a prompt, and that prompt literally contains the extracted metadata in it. And I will give it a slice of my privacy budget. This is epsilon 2. At the same time, I will train my feature generator. And then in the second phase, the generation phase, I'll poke the DP feature generator to create synthetic features. Once I have those synthetic features, I'll plug them into my DP generator model to condition it properly, and it will generate synthetic text. So I can do it many, many, many times. This is the most basic approach, and we'll extend it and expand it in a bit. But let me talk about a few of these boxes in a bit more detail. Let's start with the feature extractor that I showed on the previous slide. There are lots of ways to design this feature extractor. This goes back to the early beginnings of the talk of how do we derive insights. You could use simple topic keywords, and that's what we did with the pixel recorder team. It's a very simple feature extractor. You give it a bunch of topics that you've learned from the web about this application. You ask a model to sift through the conversations and label them. So it's basically a bit of a classification task. Or you literally give the private text, the unstructured text, to a model, and you ask it to summarize it in 1 or 2 sentences. So these are free-form summaries that are in the form of like 1 sentence or 2 sentences tops. But they're free-form. They don't have as much structure in them. They're not tabular. And the third one is the structured tabular schema, where you give the model a JSON object with multiple fields in it, and you describe each field, what it means, and what values it can take. And you then give it the text, and you tell it, I want you to extract the fields in this JSON object from the text that I'm giving you. So it's very simple. And we're going to really use just very light models. So we're using, when we did this research, it was Gemini 2.5, but it was Flashlight. So really the smallest, fastest model works really well as an extractor. Second, I want to talk about the feature generator. So this is the one that's going to ingest those extracted metadata or features and give us this DP feature generator or metadata generator. So when we use topics, it's just a simple histogram. You just need to build a histogram, and that's what I discussed at the beginning for the Pixel Recorder app. If you have these rich metadata JSON objects, you can run AIM, that's the algorithm by Brian McKenna and co-authors, and it produces synthetic tabular data with potentially many, many fields of many types, mixed categorical and numerical. And if you go with the free-form feature extractor, then you could literally do some very, very basic DP fine-tuning in order to get the feature generator. So you train a small model, 50 or 100 million parameter model, to be a good feature generator. And then with that, we could take the private features, we could take the private text, and we could train our DP conditional generator. And for this, you could either do direct prompting. If you don't want to do any fine tuning, you could just do some form of a DP-fied inference with the private data placed in the prompt, or you do the DP fine-tuning on a billion-sized parameter model. And that's the one that's going to end up being best. So let me show you some results here and ablations. We're going to use Gemma 3, 1 billion parameter model, the pre-trained model. We later on tried even larger models. Larger is almost always better, but it's an interesting ablation study that we did. We focused on the bioRxiv dataset. So this is a dataset of medical preprints, so preprints in biology. And we mostly focused on abstracts, essentially. And then we sweep the privacy budget all the way from 1 to infinity. So we tried 1, 4, and infinity. And we tuned that split of epsilon 1 and 2 between the feature generator and the conditional text generator. You need to learn how to split it. The TLDR is that you literally give the bulk of the project of the budget to the DP text generator. The feature generator needs a tiny fraction of the budget. In terms of evaluation, the metrics that we used to evaluate the fidelity of the synthetically generated data compared to the private data were the following. There's 3 of them. One is MOF score, as I discussed before in the talk, which is essentially a score of distributional similarity in embedding space. You just compute some KL distance between the distributions projected down onto lower dimensional space using embeddings. Or what you do is you extract features from both the private text and the synthetic text, and you try to compute the Jensen-Shannon distance on the features or attributes that are extracted from both sources of data. Finally, the third metric is to try to compute some sort of a classification F1 score on a downstream task. So how useful is the synthetic task for one downstream task? And what I want to highlight here is that if you look at the 3 ways of generating the metadata or the structured insights, the one that performs best is the third one, which is this JSON-rich object-based approach, and using the AIM algorithm to create the DP feature generator. It's the one that gives us the highest MOF score, so highest fidelity of synthetically generated data. And it is the one that gives the least Jensen-Shannon divergence between the attributes computed on both, and also the highest classification F1 accuracy. And also, DP fine-tuning here, the Gemma 1 billion parameter model was pretty critical. We tried, again, the other baselines, the non-fine-tuning baselines. They weren't as performant. So this already gave us a new state-of-the-art that's controllable and steerable in synthetic text generation. But one thing we noticed is the following, which is actually pretty interesting, and I want to spend a couple of minutes on it. Once you start using this conditional DP text generator, especially with high privacy, so if you go to epsilons of 4 or even 1, so in the high privacy regime, their ability to follow instructions drops drastically. Somehow DP fine-tuning or conditional DP fine-tuning makes these models not capable of following instructions as well as they would without the DP. You can see the drop from the green to the orange to the blue on this curve. So we wanted to fix this issue. And this is where Yujang came with very clever tricks and ideas that use reinforcement learning. And here's the simple idea. The simple idea is to take that conditional generator that's trained with DP fine-tuning and give it input conditions in the form of this JSON-rich object, ask it to generate, for bioarchive it would be abstracts, and then take the output of the model and extract using an off-the-shelf model like Gemini, the features that are represented in the JSON object in the input, and check, did it really follow the instruction? Did it really give me instantiations of those features that I added to the context of the prompt at generation time? And you can easily score, if you have 8, let's say, features in this object, in this case, you got only 1 of them right. So you got a score of 1/8. But if you get all 8 of them right, you'll get 8/8. this score is a reward. Notice that now we're not touching the private data anymore. We can literally play this game post all private training. So it's a post-processing on the DP5 model. And we have now a reward signal that we can use to improve the instruction following capabilities for this specific task. So this seemed very promising, and we tried it. But one thing we noticed when we tried it is this weird phenomenon, which is that once you start using RL, it improves the instruction following accuracy. This is the IF accuracy curve on the right-hand side. You see how I start with the original one that has low accuracy at epsilon equals 1, and then I bump it up to 0.61. But the MOF score suddenly drops drastically. So that quality of the synthetic data becomes really bad. What's happening is that, and this is a well-observed phenomenon, it wasn't very, I wasn't very familiar with it because I'm not a mainstream RL person, but there's this thing in RL called reward hacking, which is literally the model post RL, it learns how to get a full score on the reward rubric, in this case, just matching those metadata features without generating high quality text with high fidelity. Look at the generated text here. It's not really an abstract. It doesn't look like a rich, nice abstract. But it does have all the features that you want it to generate. So it is faithful to the input conditions that you placed in the context of the prompt. So in the literature, there are ways to fix this issue. And that is how we try to approach this problem. The design requires not just reinforcement learning. It requires doing both reinforcement learning and also some supervised fine-tuning at the same time. You have to have a weighted loss function that does both together at the same time. And this goes back to essentially OpenAI's work on RLHF, where they've noticed literally this phenomenon on reward hacking, and there was regression on some of the NLP tasks. They wanted to fix it, and therefore they used this approach. In our case, what we did is, before we even started the RL, we took the trained DP conditional generator. We asked it to generate for the same input, for the same set of conditions that we're giving in the context, multiple outputs. We did it, let's say 10 times, 50 times. So this is a little bit computationally expensive. And then we scored all the generations, all the N generations, and we took the best one. Again, this is pre-RL, so there's no reward hacking. This is still when the data output is pretty rich and representative. The MOF score is high at this point. And the best of N approach means that you're going to select the one generation that also matched the input conditions in the prompt. So now we have high quality data to do that supervised fine-tuning step. We go back, we do both now together. We do the RL step with the reward signal that I described to you, and we do the supervised fine-tuning with the best of N data that I just discussed. We do it in a weighted fashion, a convex combination type loss. And this is why we call this an anchored RL approach. Now, if you do this, the results are pretty amazing because this approach, the anchored RL approach, not only gets high MOF score even at low epsilons and low Jensen-Shannon divergence on the extracted attributes, it also has high instruction following accuracy as well, relative to the conditional model that is trained with DP without any of the RL techniques. So in closing, I really want to emphasize the importance of bringing in the context and making that context really rich. So these private insights are extremely important. And then using new techniques such as anchored RL improves the performance even more on these types of problems of differentially private synthetic text generation. There are lots of open questions here. How do we scale it to larger models? Since then, we've actually done some experiments on this front. We're going to try to add them in a revised version of the paper. But there are lots of ways in which you could advance the frontier moving from here. I want to spend just a couple of minutes on this short part before I close my talk on what can we do, again, to leverage this context matters idea, but without any fine-tuning, if we couldn't fine-tune a model. And this is an upcoming paper. We call it MAPLE, or Metadata Augmented Private Language Evolution. And I'm giving you the tiny URL in case you'd like to read it, and please provide us with feedback. It's going to show up on arXiv in maybe a week or so. So recall private evolution. We talked about it at the beginning of the talk. This is the standard approach if you cannot fine-tune a model. It has a problem, and the problem is that for it to work well, the public LLM that you're prompting needs to be trained on data that statistically is similar to the private data set. If it's never seen anything like the private data set, then it just simply won't work. How would it even generate data that's relevant for you? Now, the idea is that if you have seen a little bit of data from the private source, but not a lot, then maybe your private data appears in the tails of the distribution that you can sample from by prompting these publicly trained LLMs. So the question here becomes, can we reshape that distribution that we're sampling from via context engineering to somehow zoom in on these two left and right tail where we believe our data lives? And this is literally what we're trying to do. For example, can I give it metadata in the condition, in the context, that somehow represents the left cluster such that when I call that API, the distribution becomes heavily shifted and very representative of my left private data, and similarly for the right data? That's the question that we wanted to resolve. And we have this framework. In the interest of time, I'm not going to go into the technical details, but the high-level idea is that the exact same thing that I discussed so far, which is use a feature extractor, and now we're only going to use this rich JSON metadata extractor, run AIM, the DP algorithm that allows you to generate high-quality tabular synthetic data. But now take this metadata that's synthetically generated with DP and include it into the prompts that you use in the private evolution algorithm. So notice this is more or less the same idea, but applied with just prompting and without any fine-tuning. There are tricks here to also try to include some donated pairs of private text and metadata in the context to give the model some examples. Here's an abstract. Here's what its metadata looks like. So you kind of want to leverage the in-context learning capabilities of the model. So long story short, we tried this again on the bioRxiv. We used Gemini 2.5 Flashlight for the metadata extraction, as with the first part. We used the exact same metadata schema that I showed you before for bioRxiv, but we used a very small model as the publicly pre-trained model, as our LLM oracle. It's Qwen 2.5, not even 3.5 now, which is extremely powerful, the 7 billion instruction tune model. And so this is actually important because our approach allows you to use much smaller models, actually. And what I want to show you is that this approach which is shown in blue on this curve, improves the performance of the vanilla private evolution algorithm by quite a bit. And the improvement is drastic at lower epsilons. So you can see here that at epsilon of 2 or 1, the performance of Maple, the system that I just presented, relative to the augmented private evolution, which is the classical one, is actually quite big. That said, it is not better than the approach that I presented earlier, which is the one that uses DP fine-tuning, especially the one that uses DP fine-tuning with a context that contains the metadata, the ACTG or the ARL ACTG algorithm. So there's still a lot of room for improvement. We don't understand if this gap is fundamental or it can be closed by improving the private evolution even more. So with that, I'll stop here. And then if there are any questions, I'll be happy to take